Welcome to the course. I'm Ted, and I'll be your instructor. What is a statistic? It's just a piece of information from a large quantity of data. Simply put, a statistic describes data in some way. And in this course, you'll learn about different statistics you can use to extract insights from your data. Let's begin with averages. An average is an information reduction technique. You start with a data population, which may be too large to understand, so you need a way to reduce the amount of information into a comprehensible amount. For example, there are 126 million people living in Japan. That's a lot of people. You could look at a list of every person and their age to intuit something about the population's age. However, it's easier to take a mean average to understand the population. A mean is the sum of all observations in your population or sample divided by the number of observations in that population or sample. This is a sample of 10 Japanese ages. Summing the ages, you get 473. Therefore, the mean average is 473 divided by 10, or 47.3. Mean reduces information from these 10 observations to one value. Let's compare Japan's average age, 47.3, to Uganda's average age. The Ugandan sample sums to 158, and the count is 10. Thus, the Ugandan mean is 15.8. Comparing the two samples, Ugandans have a lower average age compared to Japan. In this example, you didn't have to compare all 20 samples to arrive at this conclusion. Simply taking an average of each was enough to help you learn about the sample differences. Another average is the median. The median is the middle number of a dataset. When sorted from smallest to largest, half the numbers are less than the median and half the numbers are above the median. The Japanese ages have been sorted. And to make it clear, the person column has the top and bottom 4 values crossed off. This leaves 47 and 48 in the middle. The median lies in between 47 and 48, which is 47.5. If our sample had an odd number of observations, such as 9, the middle number would have just been 47. An advantage of the median compared to the mean is that it is more robust to outliers. So if your dataset has any outliers, the median may be a more informative statistic. The final statistic we'll cover here is the mode. The mode is the number that appears most often in the dataset. This Japanese age sample has 48 listed twice. Thus, the mode average is 48. You can use spreadsheet functions to easily and quickly calculate the mean, median, and mode. Let's go over these now. You can calculate a mean using the average function. Here, we're passing in a range consisting of the cells B2 through B11 to the average function to calculate the mean. To calculate the median, use median, no surprise there, and use mode to calculate a dataset's mode. Let's practice calculating some spreadsheet averages. Let's now learn how to measure a data point's distance from the average. The exercises following this video will explore US train ridership to understand how it varies over time. So jump aboard the stats train. Variance measures how dispersed a dataset is from its mean. The smaller the variance, the less spread the data is. Conversely, large differences between data points increase the variance. Column A repeats with no variation. Its variance is 0. In column B, one value, 14, is different, yet close to the others. Its variance is 3. Column C has an outlier, 100. As a result, its variance is the highest among the three. To calculate variance, first calculate the mean. 10, 14, 10, and 10 divided by 4 equals 11. Next, subtract the mean from each value. For the first, third, and fourth values, 10 minus 11 is negative 1. For the second value, 14 minus 11 leaves 3. Easy, huh? In the third step, square all these differences from the average. Negative 1 squares to 1, and 3 squared equals 9. Finally, take another average of the squared differences. 1 plus 9 plus 1 plus 1 equals 12, divided by 4 equals 3. That was easy, but a bit cumbersome. Thankfully, there is a formula to calculate variance. Simply call VAR variance. Thankfully, there is a formula. That was easy, equals 12, divided by 4 equals 3. That was easy, but a bit cumbersome. Thankfully, there is a formula to calculate variance. Simply call VARP with an array, as shown in this example in which I calculate the variance for all three columns. Next stop, standard deviation. Keep in mind variance is the average of squared values. Thus, the variance is different from the original sample values, making it less intuitive. Most often, you will need to make sense of the variation by putting it in the scale of the original data. This is done by taking the square root of the variance, called standard deviation. After taking the variance with VARP, use SQRT, square root, to calculate the standard deviation. More easily, you can pass an array into STDEVP to get the same answer, here 1.73. Standard scores show you how a data point relates to the distribution. Our previous population mean was 11, and standard deviation was 1.73. Now we have a new data point, 12.73. Subtracting the standard deviation, 12.73 minus 1.73, you get back to the mean of 11. Thus, this new data point is exactly one standard deviation away from the mean. Another statistic for understanding a distribution is a percentile. Ordering a distribution and calculating the percentage of values below a specific point will tell you its percentile. This histogram visualizes 1 million values. The blue line average at 0 is the 50th percentile because it splits the data evenly. Half the points are less than 0 and half are greater. Quartiles are percentiles that segment the data into 4 chunks. The red line at negative 0.67 demonstrates 25% of the data is less than or to the left of negative 0.67. Another 25% of the data is greater than negative 0.67, but less than the blue average 0 line. The next 25% chunk of the data is greater than 0 to the right of the blue line, but less than the green line at 0.67. Finally, the remaining 25% of the data points are greater than 0.67 to the right of the green line. To get the popular percentiles in sheets, use the quartile function, accepting an array, then a number 1 through 4 to specify the quartile. As you can see here, the first quartile is 234, the second is 456, the third is 567, and the fourth is 789. Excellent progress. Now let's practice. In this lesson, you'll learn how to standardize your data. Why do this? Many real-world datasets you'll encounter will often have variables that are measured on different scales. For example, height might be measured in feet, while weight might be measured in pounds. This poses a problem because variables on different scales are harder to compare, and it may lead you to misinterpret the importance of a particular column. That column may appear more important simply because it has larger values than another, when in reality, it may actually have a very similar distribution to the column with smaller values. The solution to this problem is to standardize your data so that all your variables are on the same scale. In statistics, standardization centers a dataset's distribution around the mean of the data and calculates the number of standard deviations away from the mean each point is. You can standardize your data by calculating z-scores, also known as standard scores. Z-scores are an extension of what you've already seen in this chapter. To calculate the z-score of a data point, subtract the mean and divide by the standard deviation, as shown in this simple example here, in which we have 3 data points. First, we need to calculate the mean using the average function, and then the standard deviation using std EVP. Let's add this information into 2 new columns. To calculate the z-score, we then need to subtract the mean from each data point and divide by the standard deviation. But you probably don't want to calculate this manually as we're doing here. Just as with standard deviation, variance, mean, median, and other statistics you've seen so far, there's a Spreadsheet formula that makes it easy to calculate z-scores. In the standardized formula, you need to pass in the data point, the mean, and the standard deviation as shown here. Let's say we had another set of data points that are 10 times larger. As you can see here, while the standard deviation and mean are different, 10 times larger, the z-scores are exactly the same. Despite being 10 times larger, the distance of each point to their respective sample's mean and standard deviation are the same as in the first column, and this allows you to easily compare the 2 columns. In the exercises, you'll have the opportunity to practice standardizing your data. Almost done with Chapter 1. You're a stats rockstar already.